on the mark sheet, you will have on the mark sheet you will see that slowly I don't know if you've already seen it or not, but lab 1, your lab report mark is already up. Lab 2, the lab report mark is already up. Lab 3, I think it's not yet, right? But it's coming soon. It's already been marked. We're just in the process of uploading it. Now, in your labs, there's two components. Firstly, there's a component for your lab for in-house, what we mark you in-house, which is generally good, I've seen. Students have done well in the labs, right? The in-house mark, what we call the in-lab assessment, right? And that's out of 60 points. And your lab report is out of 40 points. And lab report was shared. So when I say shared, I mean your group just submitted one report. So if you have, let's say, Tom and Peter both in one group, so Tom and Peter receives the same mark for that lab report, all right? So we're just trying to consult with the Moodle team and have your lab in-house mark up as well. The lab report mark is being uploaded. Now your short tests. They can be picked up. One lot was available last night from 5 to 8. Anybody was able to pick their script up last night from 5 to 8? Okay, handful of guys. All right, okay. The other chance you have is if you go into the lab on Friday from 9 till 12. Did you guys probably receive a phone message, a Viber message or something along those lines? Right, so from 9 till 12, go to the ICT lab. There'll be a lab in session and the name of the person is Sumit Charan. You can pick up your script. If you have a query, make sure you check straight away, right? You won't be allowed to come back next week or 2 or 3 days time and say, hey, I need additional marks. I think I should get additional marks here. It'll be too late by then, all right? So you should get that sorted out directly in that lab, or even if you are 1 or 2 hours late, that's okay. So the lab runs from 9 till 12. That's a 3-hour slot. I don't know, what are the other classes you guys have from 9 to 12 on Friday? Even if you do have a tutorial, it's probably from 9 to 10 or 10 to 11. You still have, in that 3-hour window, some openings to go and pick your script up. So please pick up your script, and then after that, we will upload the final mark onto, final test 1 mark onto the Moodle shell. Now, guys, just to give you a head start, just a second. To talk about your project. I haven't updated it yet, but the project problem stays the same. Okay, the project problem stays the same every year. Well, as long as I teach, right? I don't change the problem. But let's have a look at the problem, right? And most of it you won't understand now. It'll sound gibberish to you, like it'll sound like garbage to you, but you won't really get it, right? Until a few, maybe 2 weeks down the line. But just to give you a head start, so this table will be updated. This table will be updated with new numbers, So you see those student numbers, you're probably looking for your student number and you probably can't find your student number. That's because this is still last year's project, right? But the problem is the same, except for every student gets a new number sequence. So let me just give you a brief rundown and then we start talking about what this is. This is a sequential logic circuit. So what we are starting very shortly, by next week Monday, we'll touch on a bit of it today. We'll finish off on adders and subtractors today, maybe a quick 10 or 15 minute each. Then I'll just introduce you to sequential logic, right? Now, sequential logic, okay, right now you have combinational logic. What is combinational logic? That means if you change the input, right? You know, you've done so many circuits, the security lamp problem from your short test. By the way, do you know the solution for that? Have you guys been able to figure out the solution? Let's just track back and just speak about the solution for that one. Somewhere here. Alright. Hey guys, this was last year's paper. How many of you were able to see this? How many of you were able to have a look at last year's paper before coming into the midterm exam? Anyone? How many? Let's see. Hands up. Hands right up. I want to see. How many of you went through Moodle, scroll down, hey, there's some midterm, there's some old short test papers here. How many of you saw the short test paper for 2018? 1, 2, 3, 4, 5, 6. Okay, 6 people out of 95. Alright. Now if you look at the question paper, it's very, very similar. So I placed my bet on the fact that I said, nah, most of the students won't check the last year's paper. So I pretty much repeated the entire, most of it. I repeated 90% of it. Okay, so instead of 57, I don't know, what number did you guys have? 47 or something. What number did you have for question 1 over here? 67, right? And then I changed a few things. This was changed. This question here, repeat. Right, question 4 was a repeat. Question 5 is a repeat. Okay, so question 5 last year, right? Question 5 last year was, let's have a read of this. 4 judges A, B, C and D sit on the appeals court bench. Normally all judges would meet and discuss their opinion with regard to a case behind chambers. So this is some story, background story. However, due to all judges traveling abroad immediately after the case hearings, the judges will avoid the current convention and have their opinion submitted via an online submission system. The case has a simple yes or no answer to the question being asked, which is on referral from the President of the state. The online submission system is a simple multiple choice, yes or no. The majority represents 3 or more judges agreeing to the same verdict. However, if a decision is a draw, the decision of the Chief Justice, Judge C, would carry weight and his vote would be the decider when otherwise the result would be undecided. Hey, that question is exactly the same as what I gave you in your midterm exam. In your midterm exam, I took out the stories of the judges and I said, hey, there's 4 security sensors and there's 1 security light. Over here it was 4 judges and they have to say whether it's a yes or no, guilty or not guilty. Alright? Okay? So, so the question is the same. The mechanics is the same. It's only I just changed the story. Right? Okay, so let's do this part here. So the answer is the same, eh? Hey guys, you can check all these other answers there. You know, I don't want to go through doing binary, conversion to binary and all that. You can just check the answers. I'll place the solutions for 2819 very shortly. Okay. So the question is this, guys, that you have 4 judges. In your case, it was 4 security sensors, A, B, C, and D, and you had a security light, right? So your inputs are 4 sensors, A, B, C, and D, and you've got a light, which is your output. So if you've got 4 inputs, obviously you don't need help with populating the input side of the table. All you got to do is just populate it according to your standard. You know, if it's 4, that means 2 to the power of 4, that means 16 combinations. So just go downwards, 16, fill up, populate those 16 lines with all the different combinations in binary. So 0, 0, 0, 0, 0, 0, 0, 1, all the way till 1, 1, 1, 1. All right, okay, let's zoom out. Okay, now let's have a look at this. There we go. Now line 1, line 0, let's call it line 0. Line 0, all judges are saying no. All security, in your case it was, all security lamps are not triggered. All security sensors are not triggered. Therefore, the light will be, no, it will be off. Obviously, nothing triggered. Now, line 1, only 1 triggered. So, majority is saying no, therefore, it will still be off. Line 2, only 1 is triggered. Yeah? So, therefore, it will still be off. The light will be off. Let's talk about the light now, all right? Same answer for the judges, same answer between last year and this year, only the story, the background story changed. Right, so line 3, 2 security sensors are triggered, 2 of them are not triggered. So it's a 2-2, it's a draw. So what do? You have to refer to what is sensor C saying. So sensor C is saying yes, right? Therefore, the final answer will be yes. The light has to come on. All right, let's look at line 4. Line 4, 0, 1, 0, 0, only 1 thing, majority says no, so light stays off. Line 5, 0, 1, 0, 1, 2 has been triggered, 2 sensors triggered, 2 two sensors not triggered, right? So it's a 2-2 draw. So what do? You look at sensor C. Sensor C is what? It's a 0. So the decision is for sensor C. So sensor C says 0 in the case of a draw, then the light will stay off. So it's a 0. Let's look at line, I'm going to jump some lines. Let's go to line number 1001. Line 9. Line 9. Right? Let's look at line 9. 1001. 2, 2. Again. Two sensors are triggered, two sensors are not triggered. Therefore, you will refer to sensor C. Sensor C is a 0 in line 9. Therefore, final output is 0. Let's look at this special case of 1101, line 13. 1101, line 13. Right? 3 are majority, but sensor C is 0. 3 sensors are triggered as 1, but sensor C, the main sensor, is saying 0. But even then, because the majority says 1, it will be triggered as 1. Alright? So that's how you go through the truth table. Right? On the right hand side, always it's always good practice that right beside, not inside the truth table, outside the truth table, you write down the min terms. Okay, what the min term for that line is. That's not the min term for the entire circuit. That's the min term for that particular input combination. Alright, so we write down the input combination, and when the output is a 0, you can write down the max term. Right? Remember, min terms only occur when output is 1. And max terms occur when the output is 0. So you write down whether if it's a max, if it's a 0, you write down the max term for that input combination. Right? So this is a good practice. What you do, it makes your work easier later on. So while you're in truth table mode, you can do all that all quickly. But don't put these equations inside. Right? This is just your like your notes right now. So the question was to write the product of sums. Product of sums, you just quickly identify it, as I said. Product of sums is max terms, right? So there you go. You just take up wherever there's a 0. We've already written it on the side of the truth table. Put it like this. Product of sums probably took you 2 lines, you know, or 2 or 3 lines of working. The next one is sum of products. Yeah? Sum of products. Right? Which is again from the truth table, wherever there is a 1. Anybody got a problem with product of sums and sums of products? No? You're right? Okay. The next one is to write the particular function as a sum of min terms. Sum of min terms, how would you do that? Well, what do? You look for the ones. Which lines does the 1 occur? So that was line 3, line 0, 1, 2, 3, 4, 5, 6, 9, 10, 12, 13, 13, 14, 15. Okay, so 3, 6, 7, 10, 11, 13, 14, 15. Maybe I made a mistake early on. Right? Eventually, you are asked to do the minimize sum of products. So what are you going to do? When you say minimize sum of products, you've got to put that into a Kano map. Right? You take your min terms or whatever you take from your truth table, go into your Kano map, then do the plot. So in this case, we end up with 3 blocks of 4, right? 3 groups of 4. And one group of 2. Okay, so we are able to find that equation. Eventually, that's our circuit. You'll get the same circuit, same answer. There can be a variation, right? There can be a variation. What I'm saying by variation is, hey, some guys would have. Would there be any other way of drawing those groups? But you will still get. Let me say this. You'll still get, the way we mark it is, even if there is a variation, because some people get some other groups, you still must have 3 groups of 4. 3 groups containing 4 members, and 1 group containing 2. So the 3 groups of 4, if you have a group of 4 in a 4x4 Kano map, that results in a min term of, can you see this? Okay, if you have a group of 4, let's say you have a 4x4 Kano map, like what we had, right? And over there you have a group of 4 ones grouped together. Okay. Therefore, the min term coming out of that would be just containing 2 laterals. Remember this term, lateral, min term, right? It will contain only 2 laterals, right? Again, so if you have 3 groups of 4, you'll have 3 groups of 3 minterms, each containing 2 laterals each. Right? Okay? So the way we mark it is, we look at your final equation, they should have 4 minterms altogether. 3 of those minterms must only have 2 laterals each, and the last minterm must have 3 laterals. So you can't be bigger than this. This is the minimized form. Alright? Depending, so what I'm saying is, maybe some guys, they drew their things slightly differently, their groups are slightly different. I'm trying to imagine how can it be different, but yeah. You still have, 3 of those minterms will have only 2 members, and the third minterm will have 3 members, right? Even if your answer is different. So you'll get it right in that case, because it's minimized. And that was your answer, guys. That was your minimal answer. Which brings us to our next question, which is what we're going to study now. So I'm going to encourage you guys, if you can help me, because I know there's about, let's see, 1, 2, 3, 4, 5, 6, 7, 8, about 30 students over here, but 35 students. But in my class roll, I've got 100 students enrolled, right? Okay, I think 2 are in Vanuatu, so okay, 98 should be in Fiji, all right? Okay. Now, out of the 98, there's only 35 attending. So now the problem is, the course is going to become difficult. So let me show you, let me draw you a graph. All right, guys. So this is what it looks like, eh? So this is weeks, right? And this is your the amount of input from your side. So student hours, right? So let's say that's week 1, 2, 3, 4, 5, 6, 7, mid-semester break, 8, 9, 10, 11, 12, 13, 14, right? So what was happening up till now is, you would see that what we were doing earlier on, like binary, conversion to binary, most of you guys are in second year, I mean all of you guys are in second year, you've got a good background in mathematics, and you know, even your high school mathematics would be able to ride you through. The energy from your high school mathematics, and even MA 111, right? Because remember, we're not doing any integration, we're not doing any volumes or surface integral or nothing difficult, no differentiation, no linear algebra, no Cramer's rule, nothing so much, right? Okay, you guys probably did Cramer's rule, Gaussian elimination, row echelon form, all that, all right? Okay, we're not doing any of that. We're doing our own sort of mathematics, which is very basic in nature. So what you guys notice is generally, you know, the learning curve was like this, and the amount of effort required, you know, not much. You know, maybe Kano maps was probably the only new thing you learned. Even a truth table, somebody would be able to just from their own natural common sense be able, without me teaching you a truth table, even me without teaching a truth table, you look at a truth table, from your common sense you'll be able to figure out what's happening over there. It's fairly common sense. Kano map is when things started to get, yeah, okay, new, right? So around about week 6, then, you know, the night before the exam, it spikes up, comes down, all right? All right, and then, all right, so this is the mid-semester break. So over here, there's too much drinking, goes down, right? Okay, right. We're in week 8 now, and people are struggling to wake up right now. So it's a bit like week 1, right? But the problem is, in the meantime, so we're going on to week 9, right? So right now, if you look at that week 8 level, it's still below week 1. Somewhere it's like back to week number 1, all right? But in the meantime, what's happening over here is, yes, okay, the effort required, what I expected you was somewhere around here, right? Somewhere around there, that's okay. Okay, and you know, that extra, if you look at the area under this graph over here, that sort of covers that particular shortfall, all right? Okay? All right? if you look at the area under that particular section over here, you take the integral, right, and you find the area and you say, okay, that covered the shortfall early on, all right. But what happens is that the course, if you look at somewhere over here, just after week 6, the course, the material started to become easy. This is when we were doing adders and subtractors, right? Adders and subtractors. It starts to become difficult. And if you now look at it, in week 8, we were looking at decoders, multiplexers, demultiplexers, right? BCD to 7-segment decoders. It's now we are applying our knowledge. Up till week 6, it was fundamental knowledge. Fundamental, basic building blocks. Kano map, binary numbers, Boolean algebra, sum of min terms, some product of max terms, truth table, how to handle that, right? Okay. Now, what's happening here is now your course will, the content, because we are using these basics, will become easy. Not easy, difficult, right? Now, the reason why it becomes difficult, it doesn't just continually climb, is because students don't keep up. They don't keep up. If you do what happened in the first 6 weeks, you know, you slack off and then you just study the night before the exam, right? Because the content was so basic, so common sense in nature, it was so common sense in nature, you can quickly, within 2-3 days, you can do a whole catch up and just go and do the midterm exam, right? And if you looked at the past year's papers, even more better for you, right? Okay. Now the problem here is it's almost like you have to keep your head above the water. We are now going to move to sequential logic. Sequential logic uses all this, but it's just like, you know, just the other lectures we did, what did we do? Decoders, multiplexers, demultiplexers, but finding the formula inside, we use all the basic stuff which you've learned in the first 6 weeks, the foundation stuff. We've learned the foundations, right? So, but sequential logic, what happens is what you will learn in week 8 or week 9, week 10 we'll use whatever we learned in week 8. Sorry, week 9 we'll use whatever we learned in week 8. Week 10 we'll use whatever we learned in week 9. All right, so it's like a building block on top of each other. And if you skip lectures, and you guys are all right, it's your friends who I'm worried about, they will start to fall behind. So even if you miss 1 or 2 lectures, you'll fall way behind because you'll be like, what is a multiplexer? Why is he using this? Because you did not attend the lecture on multiplexers, or you did not attend the lecture on demultiplexers, and that will start to affect your performance. All right. So what I'm trying to say here is, from here onwards, what happens is it will be very difficult for you to do an overnight study and just catch up on your test or whatever, right? Because the content is like a building block. If you miss out something, the next piece requires the previous piece, right? Okay. All right. Now, let's finish off with combination. I was talking about sequential logic. Now, what is sequential logic? Now, if you look at this particular circuit over here, sequential logic, this is combination logic. What we mean by combination logic? The moment you change your input, your output will change. The new process will take place. Now, in sequential logic, the new bit of information is that it has got memory. It has got memory. We will develop a memory chip, right? We will have the capability of storing something. So you can keep the memory, and it will, you know, you can store information, store bits. Well, if you can store bits, then if you have store many bits, that's 1 byte. 8 bits, you can store 1 byte, right? And if you have many bytes, you can store even more, right? So what I'm trying to say over here is that combinational is easier, sequential is more difficult, right? But the real deal of it is, most of what we use in our electronics is mostly sequential. Most of what we use in even those traffic lights, they're all sequential, all right? Okay, all right. So that's just to give you the heads up. Please encourage. I know you guys meet up with your friends in your labs and all that. Ask them next time you meet your lab partner and say, "Hey, where were you? You should come to the lectures. It's becoming harder." Right? Okay. All right. Now let's finish off on our studies of adders and subtractors. So Okay, so these two notes were not in our thing slides. We have, this is a half subtractor circuit. Okay, so we did this in week 7, guys. For those of you who missed week 7 and there was a lot of students who were absent, this is a half adder circuit, right? Just a simple circuit, 2 inputs, 2 outputs. I think you guys getting familiar with the concept of more than one output, right? That's a full adder by combining 2 half adders. I've already covered this, so I don't want to talk about this again, right? If you need help, just go and look at our video lecture, or another option is there's so much information available on the internet that you can quickly pick up on what's happening. There's so many videos and all this online. All right. Okay. Now there's something else. So that's a full adder, and if you compare this to a half adder, right? Now that's also examinable. I want to now show you, and I'll show you this picture from the textbook. What I'll do is I'll scan this particular page and I'll place it online. Okay, so this is the half subtractor. In half subtractor, there's something known as a borrow. In half subtractor, there's something known as a borrow line. Okay. All right, this is a half subtractor. Now the key point is, hey, and if you missed out the lecture, I deliberately made the slides as such so that you had to populate the answers if you were in the class, right? Okay, that's a half subtractor. That's a block diagram of the half subtractor. Then you have your full subtractor, right? That's your full subtractor, right? Okay, now full subtractor, full adder, half subtractor. We did that in week 7 for those of you probably missed out. Okay, all right, now let's come back to adder. So that's our full adder, right? In terms of a block diagram, in terms of actual circuitry, right? Okay. Where to from here? What about after you've done full adder? Now the thing about full adder was, let's talk about adders first, then we'll talk about subtractors, and then we'll finish off the lecture for combinational logic. We'll finish off the section on combinational logic, and from Monday we'll move into sequential logic. All right. Now the thing about half adder was, it could only do 1 plus 0, could do 0 plus 1, and 0 plus 0. But if you gave it a 1 plus 1, it did give a carry out. That's a half adder. It did give a carry out. But if it was sitting in the middle, it was not able to receive a carry in. Right, let's have a look at this. Can you see there's a carry, there's 2 types of carry. One is carry out, and there's a carry in. Right, so if you've got some addition like this, then it's very difficult for a half adder to do, a half adder would not be able to do it can do a carry out if you look at the line on the right hand side, on the column on the right hand side. But if you look on the line on the left hand side, the column on the left hand side, it's not able to receive that carry in. So therefore we had to build something called the full adder, right, which can receive a carry in and can push out a carry out, right. So that's why we built this truth table. So there's 3 inputs for a full adder, A, B, and the carry in, and the outputs is the sum and the carry out. Okay, so therefore a full adder is capable of doing 1-bit addition and has capability to receive carry in and can push out a carry out to the next column. Right? When you do addition, vertical addition, like how we did in primary school, you receive a carry and sometimes there will be a carry in your answer and you push it to the next column. Right? Okay. Now, that's just one bit. What if you wanted to add, let's say, the number 3 plus 6, or 3 plus 2. If you wanted to do decimal, 3 plus 2, 3 is what in binary? 1, 1. And what is 2 in binary? 1, 0. But full adder can only handle one bit. Yeah? How do you team this guy up with other full adders? Right? It's all like a building block. You see, earlier on, we made something called a half adder. Half adder can only do carry out, right? But can't receive carry in. So we upgraded our thing to this. So we use 2 half adders to make one full adder. This can receive a carry in and can pump out a carry out, and obviously there'll always be a sum, right? But this can only handle one bit addition, one column. If you look at the vertical addition, only one column, one line, right? Now, if you wanted to do 2 plus 3 equals 5, how do you do that? 2 plus 3 equals 5. 2, the number 2 is 1, 0. The number 3 is 1, 1. That's 2 bits, 2 columns, right? So you've got to now, again, in terms of building blocks, hook up our full adder with other full adders. So now I show you how, instead of redoing, I just save our time. I was going to draw this, but I think it's better I just put this textbook over here. And what I'll do is I'll scan this paper. There we go, guys. That's a 4-bit parallel adder. That is how you would hook up your full adders and half adders in order, right? Your full adders and your half adders in order to be capable of doing 4-bit. So for example, if you wanted to do 1, 0, 0, 0, that's 8 plus 7. Let's choose something easier. Okay, 8 plus 6, 101. 0, 101 plus 1, 0, 0, right? How would you do this, right? Your full adder alone can't handle it, because full adder alone can only handle one bit. It can take in a carry, it can pump out a carry, right? It can take in a carry in, it can pump out a carry out, but the sum is only happening for one bit, right? One column of bits, right? So for 4 bits, this is how it's done, guys. All right? Okay, now what's basically happening is, can you see the very first iteration, the very first one? So our addition problem is A4, A3, A2, A1. So that's like 1, 0, 0. Remember I said 8 plus B3, B2, B1, B4, B3, B2, B1, which is, I said 0, 101, number 6. 8 plus 6 should give you 14. Now, the very first round, the very first iteration, the very first entry it goes into for this particular circuit is what? A half adder. Why do you think the very first bit, the least significant bit, is being pumped into, is being connected to a half adder? This is your understanding of half adder comes in over here. Difference between half adder and full adder. Okay, somebody said an answer. I think you were right. Well, what is it? Why do you think, somebody said something here. Why do you think the first round, the least significant bit, goes into a half adder? Why not everything was full adder? Why didn't we just say full adder for everything? Yeah, so the least significant bit does not have any carry in coming in. Yeah, that's where the problem is starting off. That's the initial kick-up problem, right? Of course, the least significant bit may generate a carry out, which will become the carry out for the column, let's call it column 4, eh? Let's call it column 1. The carry out for column 1 becomes the carry in for column 2. Yeah, like what is written in the slide. If you missed out the lecture, please have a look at that, right? Okay, and the carry out for column 2 becomes the carry in for column 3. The carry out for column 3 becomes the carry out for, the carry out for column 3 becomes the carry in for column 4. The carry out for column 4 becomes the carry out for the system, right? So that's how we're doing it. We're daisy chaining it. This is called daisy chaining. Okay, daisy chaining. Daisy chaining. Oh yeah, daisy chaining. Have you ever come across, you know, like sometimes some laptops, they only have 2 USB ports. They only have 2 USB ports, but you may need more USB. Maybe you want to have your mouse you want to connect your printer, and you want to connect something else, right? Okay. So what you do is you go and buy a USB hub which has got four more ports in it, right? And let's say you were connecting many things, right? So you can connect another USB hub to the first USB hub, right? Okay? You can connect a second USB hub to the first USB hub, which connects to your port, all right? And that way you're able to have 1, 2, 3 on the first device, 4, 5, 6, 7 on the second device. So 7 additional USB ports, right? That's called daisy chaining. So that's what we're doing over here, daisy chaining, right? We're connecting full headers together. But remember, each full header is itself made up of half header, right? And each half header, according to your short test, we can build it using what? Only NAND gates. So you can build an entire calculator just by NAND gates. Just lots and lots and lots of NAND gates, right? Okay, so have a look at that. That's what I'll ask you to do is, I'll put a scan of this online, right? And I think it's also being recorded in the video right now. Now, the point here is, what you need to do is you need to cycle through, right? And it's going to take a bit of time in the lecture, but in your free time, cycle through. Let's consider that problem. 1,000 plus 0,101. Okay, so the least significant bit of A is equal to, let's say, 1,000 and B is equal to 0,101. So A1 is 0 and B1 is 1. So 1 and 0 go into A1, B1. What is the sum there? You've got to now cycle through the entire problem. You can't do the problem one shot. You have to, the output from the first block, right, becomes part of the answer for the input into the second block, right? Okay, so 1 plus 0 will give you 1. So your sum will be 1. Your carry will be a 0. How do we know carry is 0? That's from our truth table from a half header. Okay, that's from the truth table from a half header. Now, carry will be 1. The carry goes into C in for the full header, right? Carry is 0, I said, right? Now, what is A2 and B2? A2 is 0. B2 is also 0. 0 plus 0 from our truth table for the half header is 0. Carry is 0. So both answers are 0. But in the meantime, can you see the answers are being stored over here? Can you see in the bottom right hand corner it says 1s, 2s, 4s, 8s, right? And that's where your sequential logic comes in. That's storing the answer into some memory. Okay? Or you can put some LEDs there, but LEDs will only turn on until everything is there. So that's a 4-bit parallel ladder. You can similarly make an 8-bit parallel ladder. All right? Now, let me show you the next one. So, in your free time, right, just make this note in your exercise book. Cycle through 2 examples, maybe 1,000, A is equal to 1,000 and B is equal to 0,101. And you can even do A is equal to, let's say, you can give it 2 numbers, right? So A is equal to 0,111 and B is equal to 0,100 or 0,101 again, right? And just cycle through the problem. You have to see, oh, what is sum 1? So one possible exam question or test 2 question, this does not come in test 1, right? Test 2 question would be, hey, what is sum number 1? What is carry number 1? What is sum number 2? What is carry number 2? What is sum number 3? What is carry number 3, right? Okay, and so forth. I can give you a table and say, fill up this table. What is the situation in each case? All right, let me show you another variation now. We've spoken about subtractors. That's now this is subtractor. A minus B. Right, remember in A minus B there was borrow in, borrow out. Okay, over here in this book they're using the word, oh no. Don't worry about minuend and subtrend. That's basically, minuend means the first number and subtrend is the second number, right? Okay. And what you have is A minus B. You have A minus B, all right? And over here you have borrow out and borrow in, okay? Remember from our week 7 lectures, you have borrow out and borrow in, but it works in the same manner. Half subtractor and then full subtractor, full subtractor, full subtractor. So same concept. So same questions could come. That, hey, what is 1011 minus 0111, right? Okay, and cycle through the problem. Now, as a chip, you can sometimes find this particular chip. This chip here. It's called the 74LS83. Right? Now you are starting to see there's so many chips. Until the first 6 weeks you were doing 74LS, what is it? 01, 00, 02, 04, AND gates, OR gates, NOT gates, and so forth. NAND gates, right? Now you are looking at 74LS151, 74LS155, which you're doing in your lab this week. 151 and 155, right? Now have a look at this chip. This is 74LS83, and this is a chip, ready-made chip. It's got this 4-bit adder already done, right? But you've got to know how to use it. You've got to know what is sum, what is carry input, what is carry output, and so forth. Okay? Now, let me show you another one. Okay, so in your exam, I mean, you've learned about a 4-bit adder, right? If I were to ask you, hey, build a 6-bit adder, you shouldn't have any problems. There's something which you are required to have. As an engineer, there's something which you are required to have. That's called intuition, right? Remember, I've always been using this word, hey, from your intuition, what do you think this will be? You should be able to see the pattern and say, hey, okay, so if that was a 4-bit adder, if somebody asks you to build an 8-bit adder, that's what you do. You just add some more and this will be the case. So that's a 6-bit adder, 6-bit parallel adder, right? Same thing, just more full adders. Of course, you kick off with a half adder. All right, hey, what if, just like in yesterday's problem, yesterday we were discussing, hey, if you went to the technician and you required to use a 4-to-1 multiplexer, but the technician says, hey, sorry guy, I've only got 8-to-1 multiplexer. You should be able to downgrade. You should be able to use whatever he's got and downgrade that 8-to-1 multiplexer down to a 4-to-1 multiplexer. Or if you require a 16-to-1 multiplexer and he says, sorry friend, I've only got lots and lots of 8-to-1 multiplexers, you should be able to use a couple of 8-to-1 multiplexers to build a 16-to-1 multiplexer. And basically that's the problem which you have in your lab, right? This week's lab, right? That's a real design lab. So remember, our course is design. We want to do design. With whatever you've got, you want to achieve the final goal. Now, you go to the technician and you say, hey, let's say he's got these chips called full adder chips. You say, hey, I want to build a 4-bit parallel adder, and my circuit says that I need 1 half adder. Remember, the first one is always half adder. Yeah? I need 1 half adder, and I need 3 full adders. And he says, sorry, my friend, I've only got full adders. I don't have any half adders. So what do you do? What do you do? Well, basically, the first full adder was supposed to be a half adder, right? The first one, the very first adder in your system is a half adder because there's no carry in. So what you take is you take your full adder and you connect your carry in line to ground. You connect it to 0, that becomes a half adder straight away. So that's what's happening over here. Can you see? It's a 4-bit parallel adder built only using 4 full adders, right? And what did they do? The carry in for the very first one, remember a while ago, if you look at it, the very first one is supposed to be a half adder. But we don't have half adders. The technician told you there's no half adder. So for this full adder, what you do is you just connect a low to your carry in. This is how you do it in hardware. That's an 8-bit parallel adder. 8-bit parallel adder, right? This is the real deal chip, right? Real deal chip. I didn't give you a lab in, you did do a lab, but I don't know if you used the 7483 chip in lab 6, was it? Or lab 5? No, you didn't use the chip, right? We just did, we just built NAND gate or something like that. All right, okay. So can you see there's a low over there going in? That's your 8-bit parallel adder. That's 8-bit. What does 8-bit mean? That can handle 1 byte. That can handle one byte. Okay, have a look at this, guys. This is a 4-bit subtractor using full adders. That's a 4-bit subtractor using full adders. All right. Now what's different over here? Okay, this becomes a, I won't test you on this, but this is just out of interest. Our syllabus would stop. Yeah, okay. I won't test you on this circuit, but just to build your interest on this. What they're doing is, they built a subtractor using adders. Now, coming back to our original circuit, guys, what was the difference between an adder and a subtractor? Both of them used an XOR gate, right? Half adder and half subtractor. Both of them used an XOR gate. Both of them used what? Right? What did they use? So, have a look at your notes. And all they're doing here, they've introduced a NOT gate to line B. And that makes it a minus. Right? This circuit here is circuit where you can build in one circuit using XOR gate adder / subtractor. This is not coming in the exam or test. This is not examinable. It's a bit difficult for your level. I mean, we don't have time. We can go on about adders and subtractors for about 3 or 4 weeks, but we want to move to sequential logic. So that's why we'll stop it here today. This circuit here is capable of doing both addition as well as subtraction. But there's a control line over here. There is a control line over here. Add and subtract. Okay, add and subtract line. Right, so if it's a 1, it's a subtract. If it's a 0, it's an add. Okay, that's it for adders and subtractors, guys. From next week, we will look at something like this, just to let you know. This is why it becomes difficult. This is sequential logic. This is your basic circuit, it's sequential logic. Everything gets routed backwards and forwards. Until now, the flow of the bits was forward. Can you see? Up till now, the flow of the bits was forward. It just goes to the next gate for processing, next gate for processing, right? So it's a forward direction. Over here, the bits go backwards as well. Okay? All right? Comes back, and then that's where the memory is created. All right? So this is why this becomes tricky to understand. So I encourage you to attend your lectures. Please encourage your friends to attend the lectures as well. Thank you, and we'll see you on Monday. Please help your friends to come in. Thank you.